Half a kilometer of steel and glass, built in one of the most dangerous places on Earth to put a skyscraper. Taipei sits on the Pacific Ring of Fire, beside an active earthquake fault, directly in the path of the Pacific's biggest typhoons. And here is the strange part. At this height, the wind's real danger isn't a single hard shove. It's rhythm. Gusts that hit the tower near its own natural sway, each one adding to the last, until the motion grows and grows. The fix is not to make the tower stronger or stiffer. It's to hang a 660-ton golden ball near the top and let the building fight itself. This is how a swinging weight keeps a skyscraper steady, and why the famous ball you can see is not what actually saves it from an earthquake. Start with the myth. Most people picture a tall building as a rigid tower, planted stiff against the wind. It's the opposite. A super tall is designed to bend. Flexibility is its strength. A tower stiff enough to never move would crack under the loads. One that bends can absorb a gust, lean, and spring back, the way a tree rides out a storm that would snap a rigid pole. So the top of a half-kilometer tower doesn't stay perfectly still. In a strong storm, it can move on the order of a meter, back and forth by design. That motion is safe for the structure. The problem is the people inside. That slow, seasick sway is deeply unpleasant, and at the extreme, it's what you have to control. Which raises the real question: what makes a flexible tower sway so much in the first place? The answer isn't the strength of the wind, it's the timing. Every structure has a natural frequency, a rhythm it wants to sway at if you nudge it and let go. Push it in time with that rhythm, and each push adds to the last. Small, well-timed nudges build enormous motion. That's resonance. You already know it from a playground swing. You don't shove harder. You push at the right moment, and a child goes higher and higher. Timing, not force. Wind does this to a tower. It isn't steady. It arrives in gusts, and when those gusts land near the tower's natural rhythm, the sway feeds on itself. Left unchecked, wind-driven motion can be catastrophic. The Tacoma Narrows Bridge in 1940 wasn't quite textbook resonance. It was a related, self-feeding twist, where the wind and the bridge's own motion egged each other on until it tore itself apart. Same lesson. Let a structure and the air trade energy in rhythm, and the movement can run away. It's the same reason soldiers break step crossing a bridge. A marching rhythm that matches the span could build a sway that a random crowd never would. A taller, more flexible tower sways slowly. One full pass takes several seconds. Match that slow rhythm, and even a moderate wind can rock a giant. So why not just make it stiffer so it can't sway? Stiffening changes the tower's rhythm, but it doesn't remove it. A stiffer tower simply resonates at a new frequency, and it can still be driven there. Embracing a half-kilometer tower rigid enough to defeat the wind would be absurdly heavy, expensive, and still leave the top swaying enough to sicken the people up there. The real problem isn't strength, it's energy. Every gust pumps energy into the sway, and nothing is taking it back out. What a tower needs isn't more muscle. It's a way to drain that energy, to soak up the motion and get rid of it. Engineers call that damping. And the most dramatic way to add damping to a skyscraper is to hang a second, enormous weight inside it, one tune to fight the sway. Near the top of Taipei 101 hangs one of the most photographed objects in engineering, a solid steel ball, painted gold. It weighs 660 tons, about 728 US tons, and it's 5.5 meters across, as tall as 3 adults standing on each other's shoulders. It isn't cast in one piece. It's built from 41 circular steel plates, each about 12.5 centimeters thick, welded into a single mass. It hangs from thick steel cables, suspended through 5 stories, roughly between the 87th and 92nd floors. Designed by an engineering firm called Motioneering, it cost around $4 million US, a tiny fraction of the tower's price for the calm it buys. And unlike almost every other giant damper in the world, this one is on display. Right up to the observation deck, and you can stand next to it. It's become the building's mascot. Here's how a hanging ball steadies a tower. The sphere is a pendulum, and a pendulum has its own natural swing. It's tuned so its swing nearly matches the tower's sway, but it lags behind. So as the tower leans one way, the ball is still swinging the other. That means the ball is almost always pulling back against the way the tower just moved, dragging on the sway instead of feeding it. But the real trick isn't just the pull, it's where the energy goes. At the base of the sphere sit 8 hydraulic cylinders, shock absorbers, like the ones on a car. As the ball swings, it drives fluid through those cylinders. The resistance turns the motion into heat, and that heat carries the sway's energy right out of the building. The ball can travel up to about 1.5 meters before a bumper ring stops it. All told, the damper can cut the tower's sway by up to about 40%. And notice what the ball is not doing. It doesn't sense the wind. It doesn't decide anything. It's pure passive physics, a weight that swings by itself, tuned to fight. The word that matters most is tuned. A random heavy weight wouldn't help. It could even make things worse. The damper only works if its swing is matched to the tower's own rhythm. Get the tuning wrong, and it swings at the wrong moments and does nothing useful. Get it right, and the ball is perpetually a half step behind the building, always arriving to pull it back just as it leans. That tuning depends on the ball's mass and the length it hangs, which is why it's a specific 660 tons on specific cables, not just a big heavy ball. Taipei 101 even carries 2 smaller tuned masses, about 7 tons each, near the very tip of its spire to calm the slender top. This is the quiet elegance of it. No motors, no power, no computer. Just a weight, hung at exactly the right length, doing physics. Now the part the headlines get wrong. When an earthquake hits Taiwan and the ball is filmed swinging, people say the damper saved the building. Mostly it didn't. Here's the distinction. A tuned mass damper is, first and foremost, a wind machine. Wind loads a tower steadily, at a narrow band of frequencies near its resonance, for minutes. That's the perfect target for a device tuned to one frequency. The ball has time to get swinging and drain the sway. An earthquake is the opposite. It's sudden, violent, and broadband. It dumps energy across many frequencies at once, in seconds. A tuned pendulum drains a steady, repeating rhythm beautifully. It has many swings to work with. A quake gives it almost none. A sudden broadband jolt, much of it over in seconds, spread across frequencies the ball was never tuned to catch. So the ball does help a little in a quake, and it reduces the uncomfortable sway afterward. But it is not the thing holding the tower up. That job belongs to something you can't see. Strip away the glass, and Taipei 101 is built around a skeleton designed for exactly this place. 8 enormous steel megacolumns run up the tower, 2 on each face, hollow boxes filled with high-strength concrete, among the biggest columns ever put in a building. They're tied to a central steel core by outrigger trusses every few floors, deep steel arms that let the columns and core work as one stiff, redundant frame. That frame is stiff enough to resist a typhoon, but ductile enough to flex and absorb an earthquake's energy without breaking. The balance the whole design is chasing. And it's anchored deep. The tower stands on 380 piles driven about 80 meters into the ground, locking it into solid rock. This is the real earthquake defense. Mega columns, trusses, ductility, and a foundation gripping the bedrock. None of it moves an inch on camera, which is exactly why almost nobody talks about it. This isn't theory. The tower has been tested, hard, more than once. In 2002, while it was still being built, a powerful earthquake struck. 2 construction cranes fell from the 56th floor, and 5 workers were killed. The unfinished structure itself held. In 2015, Typhoon Soudelor hammered Taipei. The Great Ball swung a full meter, 100 centimeters, its biggest movement on record. And notice what caused it. Not an earthquake, a typhoon. That is the damper doing its actual job, absorbing a wind event that would otherwise have left the upper floors rolling sickeningly. Then, in 2024, the strongest earthquake to hit Taiwan in a quarter century struck. Magnitude 7.4 by the United States Geological Survey, 7.2 by Taiwan's own agency. Buildings near the epicenter collapsed. Taipei 101 stood, and footage of the ball moving went viral. But here's the tell. Even in that enormous quake, the ball moved far less than it did in the typhoon. Its biggest earthquake swing ever recorded is barely a fifth of the Soudelor record. Wind moves the ball. Earthquakes barely do, and the tower rides them out on its structure, not its ball. Taipei 101 isn't the only tower playing this game. Hanging a tuned weight inside a skyscraper has quietly become standard. New York City Corp Tower carried one of the earliest building-tuned mass dampers back in the 1970s. And later, engineers realized the tower was more vulnerable to strong winds than they'd thought, and quietly reinforced it, welding through the night while a hurricane tracked up the coast. London's Millennium Bridge had to be closed days after it opened because crowds' footsteps synced with its sway. The fix was to bolt on dampers. The pattern is always the same. You don't beat a resonance by brute force. You give the motion somewhere to go and bleed the energy away. So when you see that golden ball, remember what it really is. Not a machine that saves the building, a passive weight, tuned to fight the wind, turning sway into heat. The most impressive engineering here is a quiet trick. To keep a half-kilometer tower still, you let it move, and give it something to move against. If you want more of the machinery hiding inside ordinary life, subscribe to Beneath the Wires for more hidden engineering.